Hey guys, what's going on? So today we are going to be going over variations in the metric. This is going to be important in helping us derive other important quantities within general relativity that are going to come up later. Okay, this is going to be somewhat of a technical video. We're going to go through some mathematics and then we're going to tie it in with physics, and we're going to come to a very interesting conclusion about the affine connection, what drives changes in the affine connection, and so forth. So without further ado, make sure to hit that like and subscribe button. Make sure to go into my Patreon page if you want to support the channel and get summary sheets and notes. Now let's get straight into the topic. So at the forefront of this video, I want to mention there have been some people who have been on the comments who have wanted some more details. Some people who have really been trolling, which is kind of weird. I don't really know why people troll stuff like this. If you find this to be not up your alley, you don't really have to watch it, right? I'm not really in this to entertain trolls in the comments. I don't really know why someone would troll physics videos. That seems to be more of a political thing, but anyways, we are going to get straight into variations on the metric. So last time we covered two ways to derive the geodesic equation. So, and those two ways were the Einstein equivalence approach. The other way was the Lagrangian approach, where we said the Lagrangian was equal to the square root of the metric, okay, times the velocity, two components of the velocity vector. So let's now get back to discussing the metric tensor. So, as we recall from a couple of videos ago, our metric tensor really told us everything about space-time at some point. It was something that helped us understand distances between two events in space-time. So from a couple of videos back, we can imagine we are near a black hole. Just suppose you're near a black hole or anywhere on a manifold, okay? Or anywhere in space and time. You're holding a ruler and you're holding a clock, okay? And that's all the information you need to know to measure everything in your laboratory at that moment in space-time. Okay, and okay, so suppose we're here near a black hole, and the idea here is that the metric changes as a function of where you are relative to that black hole, or where you are relative to really anything, right? This is general relativity. When we're talking about being near a black hole, though, space-time is going to warp and change dramatically, okay? And depending on the radial distance you are from the black hole, this metric is going to have different values, okay? We're going to be talking about the Schwarzschild metric, we're going to be talking about the Kerr metric, the Reissner-Nordstrom metric, the Kerr-Newman metric, and we're going to also be talking about metrics for really elementary wormholes also, which is going to be quite interesting. So, that was the metric. The metric tells us everything we need to know about geometry at some point, and then once we know that, we can know really everything else, be able to conduct a laboratory experiment at that space-time point. And so the metric is a function of our space-time coordinates, so that this is really how we write it, and therefore we can take the derivative of g alpha beta with respect to mu. Okay, so this is going to change as we travel along the coordinates, okay, and we can take covariant derivative of these guys and calculate that change, okay. But we also want to know something else about the metric. The metric can be written as a matrix. So the natural question is now, okay, what about the determinant of the matrix? What about the trace of the matrix? Right? How do those guys change? Okay, and that's what we're going to take a look at in this video. And what we're going to be able to find is that the determinant of the metric can be calculated in a specific way, and that the determinant of the metric drives changes in certain components of the affine connection, not all of them. So let's see how this works. Okay, so we said that the determinant of the metric is the determinant of some matrix, okay? And that matrix now we are going to literally take as a matrix, okay? The metric doesn't necessarily have to be taken as a matrix, but it can be encapsulated into a matrix, which is nice. And so we are going to take this for what it is now. This is a mathematical object. It's a matrix. We can Taylor expand this matrix as well. So, and this is something you probably see in quantum mechanics. So when you Taylor expand an exponential, you get this, which can be summated to look like this. And so we're going to define this guy as B. And so this is our fundamental relationship. So we can also write A is equal to the ln of B. Right, so this is another way of writing that. We can also understand the trace and the determinant of the matrix. And we're going to string things together here. So this guy here is our matrix. Here's our A matrix. Our trace of A is just going to be the sum of these two. So again, if you can diagonalize, and you can diagonalize almost any matrix, right? There are some things, some matrices you can't, obviously. But if it's just if it's a matrix that can be diagonalized, then the trace is going to look like this. And so the exponential of the trace is going to look like this. The determinant of our exponential looks like this, right? And so that's equal to this. So that means that the determinant is equal to the exponential of the trace, right? Because these two guys are the same, right? So we take these equations up here and put them together, and what we get is this here and this here, right? So the determinant of B, we said was B, is equal to the trace of the ln of B, because A was the ln of B, as we said up here. Okay. We take the natural logarithm of both sides, and the natural logarithm of the determinant of B is now equal to the trace of the natural logarithm of B, right? Because the ln of the exponential is just the exponential part, right? The derivative now, so taking this, the derivative, or the integral of 1 over x dx gives us the ln. So this is sort of going backwards almost. So we can sort of think of this as going backwards. But we can realize that this here is equal to this, and this here is equal to this. So this is where we're going to identify B. We're literally, at this point, we're literally identifying the metric as a matrix, okay? Again, we don't have to think about the metric as a matrix, and oftentimes it's not very useful in thinking about the metric as a matrix, but we can nevertheless. And what this means is that we have the determinant on one side, and we have the components on the other side, with this guy being, with G alpha beta being equal to the inverse of B, okay, and then G equaling the determinant. Oh wait, the determinant of B is equal to G with no indices. So we have the determinant on one side of the equation and the components on the other side of the equation. And this is what I was talking about earlier when we asked how the determinant of the metric changes. And this is how we can calculate the change in the determinant, where this change here, right? We just want to keep in mind that when we see this change right here, that means that's a sort of a total. This is a total change in the metric. So this total change in the metric is equal to this derivative in the metric over all the possible components on the manifold. All right. Same thing goes for this guy. All right. So here's our equation. We can multiply both sides by G, because again, that's just a number. we can also realize this guy here, the derivative of this guy here is going to be, because it's a square root, we have this right here. And this is really just chain rule, right? So this is chain rule. And so we get that this guy here is equal to this, which is what we're doing here is, right, so this guy here is this guy right here. So this is this is the yellow. Okay? And we now take the negative right here. G is equal to the square root of G squared. We can cancel out one of these square roots, and we get this guy. So this is really the point. We can change this guy a little bit by saying that the derivative of this guy is 0. And when we do that, again, this is product rule, and we find out that this here is true. And so we can do some substitution and get this guy right here. All right. I tend to, so this here, you can use either of these. I like to modify it a little bit just to remember things a little bit, where we have determinants on one side and components on the other side. But this, again, we're just multiplying both sides, or dividing both sides by the square root of G. Okay. And then you can multiply by 2 if you want, but that doesn't really matter or mean anything. So we have the determinant here on one side, components on the other. This is how we calculate this is how the determinant of the metric is related to the components of the metric. Right, and this really holds actually for any, if you actually think about it, this actually holds for any matrix. We identified B as the metric tensor, but nothing would stop us from saying that this is just some arbitrary matrix. Okay. So this result's going to be important for understanding this guy right here. This guy right here is a little bit different than this guy right here, because these two guys are the same. So this is a subset of components within all of these components that are unique, and we'll see why. The result here is going to be that these guys are calculated just by changes in the determinant of the metric, whereas these guys here, they're determined by changes in the components. So what that means is that changes in the determinant drive changes in this guy, and changes in the components drive changes in this guy. So sort of pictorially understanding this, we have G delta alpha gamma, where delta does not equal alpha, does not equal gamma. And then we have our subset of guys in here. We have delta, delta, gamma. And so these guys in here are unique in that we are going to be able to see that these guys, when you traverse yourself along the manifold with that metric in your hands, some of the connection coefficients are going to transform. They're really only dependent on transformations in the determinant of the metric, not in any of the other components, or not in any other ways of the metric. So let's go ahead and do this now. So we're going to derive this conclusion. So we have this guy here. So this is what we want to recall. This is what we established before. Again, we said that these guys were just derivatives, total derivatives. And to get from here to here, well, we've kind of done this before when we took a look at deriving the intrinsic formula for the Christoffel symbols. I did this in my tensor calculus playlist. I believe I also did this when we were talking about deriving the everything about the Christoffel symbols. And so we get, we kind of went through this. This was the metric compatibility argument, where we were able to bring E alpha over to this side of the derivative. And in doing that, we get this, right, because these guys are Christoffel symbols, or these are the connections, and then these guys are the metrics, right? So we have this now equaling this. So we can make that replacement, and then we multiply G alpha beta, again my apologies for the dog barking, through all of this. We get our Kronecker deltas, okay, because we have some contraction going on, right? So contraction with the beta, then we have alpha delta, beta delta. Again, my apologies for the dog barking in the background. Hopefully the mic doesn't pick up that as much as I would like it to. But anyway, so we have this. So we can change now, since this is Kronecker delta, these guys right here. All right. So what we have is the change in the determinant of the metric, which is right here, is equal to 2 times these guys. Again, I think the dogs have met the mailman, so just bear with me on this. And so we have, this guy. We can divide both sides by 2g, and now we have this. How did I get from here to here, right? This was just, again, this is the definition of the derivative of the natural logarithm. So we have this. To get from here to here, again, we just take that derivative now of the logarithm, and we get this. All right. And the 2, right? The 2 here is because of the square root. Okay. So this is it, right? That we have changes in the determinant. We have a change in the determinant of the matrix divided by the determinant, and that gives us that drives changes in this guy right here. So this guy here is given to us just by determinant. This guy here is given to us by derivatives in the components. I'm almost done with the video, so hopefully you don't get a lot of the dog barking in the background. But this is the point, right? The point here, again, is that, I don't really want to say drives changes, actually, because these aren't derivatives. We could take derivatives of this. Well, you could take derivatives of this, and you just be taking derivatives of this as well, and you'd be taking a derivative of this, right? So this guy is going to drive changes in this subset of connection components, whereas the rest are going to be driven by the components of the metric themselves. Anyways, so that's the point we want to get to here. That's the point. And with that being said, here I'll take us back down to the 2 equations. This here was something we derived earlier when we talked about the Christoffel symbols. But now we have this guy at our disposal, and that'll be important to you to remember for later. So with that being said, I hope you guys enjoyed this content. Make sure to hit that like and subscribe button, and I will see you guys in the next video.